This is the second part to 7.17.2 exponential growth and decay lesson, because we had to kind of stop it after graphing, but now we're going to be doing exponential modeling. So these are actually the same formula. Y equals a times 1 plus r to the t power, and y equals a times 1 minus r to the t power. A is going to be our initial value. A is the initial amount of whatever we have. These are all going to be applications, by the way. R is our percent, but we have to make sure we write it in a decimal form. And then T is time, generally in years, but not always in years, so it depends on whatever they're measuring in for the problem. Like if it's a bacteria question, who knows? Alright, so let's take a look at whether we should use 1 plus R or 1 minus R. We're going to be looking for keywords like growth and decay. So if it's growing, you're going to be using 1 plus R for your base, because that means you're increasing it over 100%. And then decay, you're going to be using 1 minus R for your base, because it's going to be decreasing away from 100%. So this question says a scientist estimates the specimen begins with 730 bacteria, so that's our initial value A. And it grows, so there's a keyword there for using the growth formula, by 35%, so that's the R. So writing our equation, and they started with capital A for amount. It doesn't really matter, Y, capital A, whatever you want. But the initial amount, the lowercase a for this formula, was 730. And then we're growing, so it's 1 plus 35% is 0.35 to the t power, x power, whatever you want to say. So this next question, we're going to have to utilize our calculator. We will eventually learn how to solve this algebraically, but it does say underneath my screen here, I want to know when the population reaches 9,000. So on our calculator, we're going to type our function into y1, which was 730, and you don't even have to simplify it. 1 plus 0.35 is 1.35, but you don't have to do that. And then to the x power, since that's the input variable they use for our calculators. And we're going to go to our table. Now if your table is not in automatic fill mode, remember you have to go to your table set and change it to autofill. But mine's already there, so going back to my table, I'm looking for when the population of the bacteria reaches 9,000. So the blue column, the Y column, is the population. So I'm going to have to scroll down for a little while. Remember I have a bit of a lag on mine, so it's going to take a minute. Keep going. Oh, passed it. Alright, so 9,000 would have reached, let's see. Where are we at? Come on, cursor. So 9,000 is between 8 and 9. And remember, this problem wasn't measuring in years because it was bacteria growth, but it would have fallen right between here. So for our answer, for now, for Algebra 2, our answer of between 8 and 9 minutes is a good answer. So that's what I want you to write down. Just make sure you're labeling properly, because this was measuring in minutes because it's bacteria and it grows really fast. Alright. This next one, we buy a car for $36,000 and the value decreases by 14% every year. So this $36,000 is the initial value that we're going to put into the front of the function. And then it's decreasing, so we're going to use the 1 minus r formula. And then our r is 14%, which we're going to write as 0.14. So write the exponential decay model first. I'll use y equals 36,000, 1 minus 0.14 to the x power to the t power, whatever you want. And then it says evaluate after 3 years. There's a bunch of ways we can do this, guys. So x equals 3 is the idea. You can either manually plug in x equals 3, or you could go to your calculator, because we're going to have to use it on the next one, and figure it out from your table. So I like using my calculator. I'm going to plug it into my calculator. That's 36,000. And then 1 minus 0.14. Close the rate, and then raise it to the x power. So, back to my table. I believe the question was after 3 years, so if you scroll down to 3 years, now don't just tell me 22,898, because if you actually go and highlight that blue value, there's some change associated with those dollars. So it's 22,898 and 2 cents. Just to be really nitpicky, right? That's what we're going to write down for x equals 3. And then it says estimate the value for when it's $15,000. So this is just like that bacteria question. When would it have hit $15,000? Pretty much in between 5 and 6 years. So between 5 and 6 years is a good answer. Alright, oops, no. Back up here. Alright, so those answers were, I forgot what they were. Hopefully you wrote them down. Alright, next question. The growth of an antique table since 1975. Okay, can be represented by this equation. So I already gave you the model, and that model tells you a lot of stuff. So remember the number in front of your model, in front of your base, this is the initial value. So when it says, what was the table worth in 1975? They're asking you what was the initial value, so $325. And then the rate of growth is kind of sort of in this base. Remember, this is 1 plus the rate of growth. So this is really 1 plus 0.03. So if I asked you how fast was it growing, that's the 0.03, but a better answer would be 3%. Now, you can write 0.03 as well, but what you cannot write is 0.03 with a percent sign after it. That means something totally different. So choose how you want to write your answer. Alright, now for my favorite formula. Compounding interest. So this formula looks really scary. There's still a value in front of the base, which is the initial principal this time, because these are usually associated with like bank accounts. So initial principal is what you invest initially, and I can't read what that says, but I think it says R is the annual interest, written as a decimal again, and then N, this is a new one, it's how many times you collect interest in every year. So these accounts are going to compound, quarterly or daily or weekly. So when I think about what my N is for each problem, it's going to change depending on what keyword they tell me there. And then T is typically measured in years. Sometimes not, though, so watch your labels, okay? So this question says we invest an initial or deposit $1,000, so that's that initial value, the principal they call it. And it pays 8% interest. Find the balance after 1 year, so that's time. But then they're going to change the compoundings. So for annual interest, that means you collect interest once. For quarterly interest, that means you collect interest 4 times. And then for daily interest, technically it's 365 and a quarter, but we'll just say 365 to keep things easy. Alright, so in our home screen of our calculator, we don't need to use a table here. We're investing $1,000. 1 plus 0.08 was our interest rate as a decimal, divided by 1. And then up in the exponent here, it's 1 times 1 year, because that N shows up 2 times in our formula, here and here. So if I was to type this in my home screen of my calculator, which there's a lot of things within that formula I didn't have to type, like all those ones are negligible. Like this divide by 1 I don't have to do. And also this raised to the 1 times 1 power, it's not really necessary, because 1 power doesn't do anything. But whatever. I get 1,080. So we collected $80 in interest, which is actually pretty decent. So what happens if I change this to quarterly? So all of those N's are going to change to 4s. So there's 2 places the N shows up in this formula, right here and right here. So on my calculator, you can just pull up to the previous entry and hit enter over it, or you could do second enter to bring up the entries and change this one to a 4, and then change the other divide by 1 to a 4. And we're going to get a little more money. $2.43 more. Alright, so $1,000. $1,082.43. And then I believe it changed it to daily was the next one. So for this I'm just going to retype it. The digits overtype, so if you have to do like 2 extra digits you'd have to insert them, and that's a pain in the tushy, so I just don't do that. 0.08 divided by 365 for daily. Close that base, raise it up to the 365. I'm going to say times 1 just for the sake of habit, but 1 year doesn't really do much. We often will leave it in for more than 1 year. Okay, cool, another dollar. Alright, the $1,083.28. Alright. So jot those numbers down, and it does change over time and depending on how often you collect interest. So if given the choice, if nothing else is different on your loans, you want to go with the investment that gives you the biggest payout. So, this question is a little tricky because they seem to be missing some information. So how many years will it take my account to double if it collects 4.5% interest and it's compounded monthly? So we're still going to use this same formula we have been using, but it seems like they didn't give me any money to invest. So in this case, you just get to make up whatever amount you want because it's not going to matter. So $100 seems like an easy amount of money to invest. So let's do $100. And 1 plus my interest rate is remember move it 2 spaces or divide by 100, 0.045. Collected monthly, so that's the n is 12 this time. And then up in the exponent, this 12 shows up again, and I don't know the time, so I'm going to leave it as x. And we're actually going to have to use our calculator here, right? So I'm going to type this into y1, and I'm going to figure out when my money doubled. So if I invested $100, I'm going to be looking for a target value of $200. I forgot what it was. 4, 5. Got it. Compounded monthly, so divide by 12. And then close the base and go up to the exponent and make sure your 12 times x or 12x is in the exponent position. If you're using an older calculator, make sure 12 times x is in parentheses. And then I go to my table and I'm looking for my money to double. So I'm looking for $200. I got to get down past 10 years apparently. There it goes. Alright, so it doubled right after 15 years. So you can say 15 to 16 years would be a good answer. We're just looking for an estimate answer at this point in Algebra 2. Eventually we'll learn how to solve them algebraically and be more exact. Okay. And then for my favorite formula, continual interest. So literally it's collecting interest at every moment of every day. And this is the formula we're going to be using. It uses our friend, you haven't learned about him yet, but he's the number e. E is a number. It's like 2.718 roughly, just like pi is a number. So the base, instead of 1 plus an r, we're going to use a base of the number e. So it's still principal times this new base e, and then to the RT power this time. So whatever the rate is times time. So $1,000, 8% 1 year continual interest would be 1,000 times e, and then up in his exponent, 0.08 times 1. So the place you find e on your calculator, a couple different places. He is, I don't need to be on my table. He is above what we call the natural logarithm button right here, e to the x power, so that'll bring up an exponent with it. Or if you just want the number e, it's right above the division sign. So if you use, oops, not that. Clear. Alright, I'm crashing my thing here. If you do second division, yeah. It'll bring up what e is, which is 2.718 roughly. Clear. There we go. Second division. Apparently I hit 2 things. There we go. 2.718 as promised. Anywho, I don't even like that button. I like to use the one above the natural log because it carries an exponent with it. So it was $1,000. You don't even have to hit a multiplication sign. If you pull up the e next, it'll know to multiply them. And then it was 8% for 1 year. So 0.08 times 1. And it gives you $1,083.29. Okay. So even though you're collecting interest continually, it doesn't give you that much more money because we're not collecting interest that often. Alright, for the sake of time, we're going to jump down to number 20. And this is going to be, we're going to use our graphing calculator because I don't know the answer and I'm going to have to estimate it. So we want our account balance to triple this time if it collects 5% continuously. So I am going to use this PERT formula. And just like on the other question where they didn't give me a value, I get to just make up how much money I invest. So let's invest $100. And then if it's continuous, it's E to the 0.05, I don't know time, so I'll leave it as x. So I'm going to type this into y1, and then we're going to look at our table to see when it triples, so I'm looking for $300. Dream big, kids. Alright, 100. And then you can say times e, but it doesn't matter, e to the 0.05x power. Make sure that's up in the exponent, either in parentheses or just up in the exponent for the newer calculators. And remember, I'm looking for triples. So, after scrolling for the rest of my life, 22, really close to 22 years. So I'm just going to put that down. I'm going to say about 22 years, because it is definitely an estimate. But for Algebra 2 right now, there you go. And it didn't matter how much money you invested. If you did $1,000 and looked for $3,000, it would still be 22 years. Okay. For the sake of time, I'm going to end the lesson there. We're going to do lots of practice with this, so good luck.